Okay, we're starting chapter 4. We're really getting into it now. You can tell by the title of this lecture that things are getting more serious. Okay, and I want to think about probabilities with you. What do we know about probabilities? We know that probabilities are always between 0 and 1, inclusive, meaning they can equal 0 and they can equal 1, right? Every probability is somewhere in that range. And we also know that if you add up the probabilities of all of the outcomes in an experiment, the probabilities will always add up to 1. Like flipping a coin, there's 2 outcomes, head, tails. They each have a probability of 1/2, which is between 0 and 1. And if you add those 2 probabilities together, you get 1/2 plus 1/2, which is 1. Think about rolling a die. There are 6 numbers. The probability of rolling each number is 1/6, which is between 0 and 1. And if you add up the probability of a 1 plus the probability of a 2 plus the probability of a 3 plus the probability of a 4 plus the probability of a 5 plus the probability of a 6, then you will get 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6, which equals 1. Okay, so let's write this down. Probabilities always lie between 0 and 1, inclusive, and add up to 1 when we add the probabilities of all possible outcomes. So, any function that does these 2 things, any function that lies between 0 and 1 inclusive, and also when you add up the outcomes of every possible element in the domain adds up to 1, then that function could be used to calculate the probabilities of certain events. Okay, so let's write this down. Say any function, let's just say f, okay, any function f that satisfies these 2 things. F of x is between 0 and 1 inclusive, okay, that's for all x, and number 2, the sum of f of x for all x equals 1. Any function that satisfies those 2 things satisfies the 2 things for probabilities. And so any function that satisfies those 2 things could be used to calculate probabilities of certain experiments. And so a function that does those two things right here has a name called a probability density function or a probability distribution. Okay, so any function that does those is called a probability density function, or a probability distribution. The book says probability distribution function, but in my experience, when you use the word distribution, you most of the time do not put the word function after it, but it's fine if you do. Okay? And again, the reason why we call those functions probability density functions or probability distributions is because those functions can be used to calculate probabilities. So I'm going to show you one in particular today called the hypergeometric density function. Okay? I need to cover a few things with you first. Okay, so first we need to talk about factorials. That looks like this. A number, what should we call it? We can just call it x for now, with an exclamation point after it. We only do this where x is a non-negative integer. So that means 0 or 1 or 2 or 3 or something like that. Okay? All right. You may have seen this before, but this is just in case you haven't. So, what does that mean when you see a number followed by an exclamation point? If the number is 0, if you have 0, the exclamation point is called a factorial symbol. So you would see that, you would say 0 factorial. Okay, so that is defined to be 1. No reasoning for it is given. That's just the definition of 0 factorial is 1. Okay, now, if 0 is any integer bigger than 1, if x is any integer bigger than 1, then its factorial is the product of all of the integers from 1 to x. So what that means is this: 1 factorial also equals 1, just like 0 factorial does. 2 factorial equals 1 times 2. Some people write 2 times 1. That's fine. It doesn't matter what order we write them. But the point is that it equals 2. 3 factorial equals 1 times 2 times 3, which is 6. 4 factorial equals 1 times 2 times 3 times 4, which is 24. 5 factorial is 1 times 2 times 3 times 4 times 5, which is 120. Okay, and so on and so on. These numbers get pretty big pretty fast. If you just went only 4 more to 9 factorial, already be up to, let me just write this down, that would already be getting up to 362,880. So you can see that factorials get big fast. Factorials work very nicely when you're dividing one by another. Let's look at this. What if I put 100,000 factorial divided by 99,998 factorial. Now, these numbers, if you look at this guy up here, 9 factorials this big. Imagine how big these factorials are. They're astronomically big. You would not want to calculate this fraction by calculating those two numbers individually. No way. But you don't have to, because when you divide a factorial by a factorial, so much of it cancels out. Let's look at the bottom of this fraction first. The bottom is 1 times 2 times 3 times 4 and so on up to 99,998. The top is 1 times 2 times 3 times 4 up to 100,000. So that's gonna go past 99,998 and past 99,999 and stop at 100,000. Okay, well, look at this. 1's cancel, 2's cancel, 3's cancel. The first 99,998 numbers are going to cancel. And what are we left with? We are left with 5 9s followed by 5 zeros, because all I have to do is multiply those two numbers together, because they're the only thing left. Here's our answer. So the answer is 9,999,900,000. It's a big number, but the math that we have to do to get that is math that a 4th grader could do. Okay? All right, so that's factorials. Now, let's talk about combinations. So let's ask this question. How many ways is it possible to draw, let's say, K particular objects out of a group of n total objects. So what I mean by that is, suppose you have 10 coins in your pocket, and you say, if I reach in my pocket and grab 2 coins, and I wonder about those 2 coins both being dimes, or maybe both being nickels, or anything like that. Let's not worry about what they are, but Just, you have 10 coins in your pocket and you're going to reach in and grab 2 coins. And you're wondering, what are all of the different possibilities of what I might get? How many different possibilities are there? Okay, that's called a combination. And you would say this, you would say n choose k, meaning I have a total of n objects and I'm going to choose k of them. So obviously n and k both have to be non-negative integers, and k cannot be any bigger than n. Okay? And the answer to that question, how many ways is it possible, is actually very easy to calculate. The answer is n factorial divided by k factorial times n minus k factorial. And we have a symbol for that. And the symbol is 2 very tall looking parentheses, and you put an n over a k. No line between them, not like that. It's not a fraction. There's no line between them. Some people do this. They write a C for a combination, and they put an n here and a k there. That's also an acceptable symbol, but I'm going to use this one because that's what it is in the book. Okay, so let's do that question about coins in your pocket. So if you have 10 coins in your pocket, and you grab 2, how many possible combinations, let's call them since that's what they're called, are there? Okay, so it's very easy to answer. We write it this way, 10 choose 2. Okay, and it's just 10 factorial over 2 factorial times, what's the last number? 10 minus 2 factorial, so that would be 8 factorial, right? Now, this is really easy. I can tell you right now the answer is 45, and I didn't memorize that. I just computed it while I was talking because it's very easy, because of the cancellation like I showed you up here in this problem. Okay? Take the largest number on the bottom. Sometimes the first one's bigger, sometimes the second one's bigger. Whichever one is bigger will cancel out the most stuff from the top. So I'm going to write it out, but you'll find very quickly that you don't even need to write it all out. You can do at least half of it in your head. What I mean is, let's write out the top. 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. And on the bottom we have 2 factorial, 1 times 2, times 8 factorial, 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. Now you can either look at this group of numbers, 1 times 2, and cancel out the 1 and 2 on the top, or you can look at this group of numbers. My advice is look at the larger group, whichever one is bigger, 2 factorial or 8 factorial, because the bigger one will cancel out more stuff. And here's what you do. 1's cancel, 2's cancel, 3's cancel, 4's cancel, 5's cancel, 6's cancel, 7's cancel, and 8's cancel. The only thing left on top is 9 times 10, which is 90. And on the bottom is 1 times 2, which is 2, and 90 divided by 2 is 45. See how easy that is because of the cancellation, which you are guaranteed. to have a lot of cancellation. Okay, I'm going to erase that. And show you that here's how I do it in my head, okay? I say, okay, that 8 factorial will cancel out the first 8 numbers in here and leave me with only the 9 and the 10. So you don't have to do it in your head, but I'm saying if I do that, if I think of it that way, then there's not much left, and it's easy for me to do in my head. So that on the top will just be 9 and 10, and on the bottom the 8 factorial is gone. I just have 1 times 2 left. Okay, and then there's not much left. You can do the rest easy. You got 90 over 2, which is 45. I even go a little further. I even then say, oh, 2 goes into 10 5 times. So I have 9 times 5 over 1 times 1. It gives me 45. But you don't have to do that if you don't want to. Okay, so that's how you do combinations. All right, so now let's talk about poker. Okay? When you play poker, even if it's 7-card stud or Texas Hold'em, which you get 7 cards, a poker hand is always 5 cards, right? If you're playing 5-card poker, then you just have 5 cards. If you're playing 7-card poker, you get 7 cards, but you have to pick the best 5. Okay? And you probably know that there's a hierarchy of hands. Like the best hand is called a royal flush. Okay? And there are flushes, straights, full houses, 1 pair, 2 pair, 3 of a kind, 4 of a kind, you know, and certain hands beat other hands. How is it decided which hand wins? Well, there's a list. I mean, most people memorize the list or print out a thing that says this beats that. But the point I'm trying to make is, how was that decided in the first place? It all goes off of probabilities. Royal flush is the best hand because it's the hand with the smallest probability. So it's harder to get. Okay? 1 pair is not a very good hand because it has a very high probability. It's not hard to get a pair of cards. Okay? So how do they calculate those probabilities? Well, that's exactly, they use this function called the hypergeometric distribution. Okay, but let's not, I don't want to just say here it is, and it's called the hypergeometric distribution. I want to actually show you how to calculate a probability like that. So here's what we're going to do. Suppose that you're going to draw 5 cards out of a deck of 52. Without replacement, right? Because once you draw a card and put it in your hand, you don't put that card back in the deck. So we're going to draw 5 cards out of a deck of 52 without replacement. And we are going to calculate what's the probability of getting a pair of aces, let's say. Okay, so I'm going to write this question down. If we draw 5 cards out of a 52 card deck, what is the probability of drawing exactly 2 aces? Exactly 2. So 3 is not what I'm concerned about. 4, I mean, if I'm playing poker, 3 or 4 aces is better than 2. but this question is asking 2 and only 2 aces. Okay, so let's figure this out probability wise. Okay, so that means drawing 2 aces and 3 non-aces. Okay, so let's make sure that you understand that's important. So this means drawing 2 aces and 3 non-aces. Now remember, to calculate basic probabilities, you divide how many ways it can happen divided by how many total possibilities there are, right? Like, for instance, when flipping a coin, the probability of getting heads is a half, because there's 1 heads and there's 2 sides of the coin. So the probability is 1 over 2. If you're rolling a die and you say, what's the probability of rolling a prime number? That's also 1/2, because there's 3 prime numbers, 2, 3, and 5, and there's 6 numbers total. So the probability of getting a prime number would be 3 over 6, which is 1/2. So to calculate probabilities, you divide how many ways it can happen by how many different total ways there are. So in this case, we have to ask ourselves a couple of things. How many ways can 2 aces be drawn from the 4 aces in the deck? We'll answer that in a minute, okay? And then we need to ask, how many ways can 3 non-aces be drawn? So that means, how many ways can 3 cards be drawn from the 48 non-aces in the deck? And one more question we need to answer is, how many ways can 5 cards be drawn from a deck of 52? Okay, let's answer those 3. There are 4 aces in the deck, and you're wanting to draw 2. I mean, that's what we're calculating. So, how many ways can I draw 2 out of 4 aces? The answer is this: 4 choose 2, which we know is 4 factorial divided by 2 factorial times 2 factorial, and that's going to equal, think about it, isn't that going to equal 3 times 4 over 1 times 2? which is 12 over 2, which is 6. Let's enter the next question. How many ways can 3 cards be drawn from the 48 non-aces? Well, that is 48 choose 3, which is 48 factorial over 3 factorial times what? 45 factorial. And that's not as hard as it seems. Isn't that just 46 times 47 times 48 divided by 1 times 2 times 3? Which you're not going to do in your head, I understand that. That's still a big number. Comes out to 17,296. And the third question. How many ways can 5 cards be drawn from a deck of 52? Well, that's just 52 choose 5, which is 52 factorial over 5 factorial times what? 47 factorial. And isn't that just 48 times 49 times 50 times 51 times 52 over 1 times 2 times 3 times 4 times 5, right? You can use a calculator for that. Surprisingly, the result is very small. It is 10. Oh, I'm sorry. Never mind. I typed in the wrong thing into my calculator. It's way bigger than that. I said I was surprised that it was so small, and that's because it was wrong. The answer is actually 1,326. Okay? So now, to find the probability of drawing exactly 2 aces, all we have to do, here, let's go ahead and write this. Probability of drawing exactly 2 aces. That just equals the number of possible ways to draw 2 aces and 3 other cards divided by the number of possible ways of drawing 5 cards. I'll write that down. You don't have to remember it. Okay, it equals number of ways to draw 2 aces and 3 non-aces divided by the number of ways to draw 5 cards. So that is 4 choose 2 times 48 choose 3. So this is drawing 2 of the 4 aces, and this is drawing 3 of the 48 non-aces. That's on top. And then we divide that by 52 choose 5, which is the number of ways of drawing 5 cards. Okay? So looking at the numbers that we wrote down earlier, that is on top 6 times 17,296, and on bottom is 1,326, and this comes out to equal a surprisingly large number, 2,598,960. Okay? So now, let's figure out the answer to our question. What's the probability of drawing exactly 2 aces? Okay, we can write this down now. So the probability of drawing exactly 2 aces equals, it's a fraction, okay, it's the number of ways to draw 2 aces and 3 non-aces divided by the number of ways to draw 5 cards. And so that equals exactly this. Drawing 2 of the 4 aces, you can do it that many ways, which is 6. Drawing 3 of the 48 non-aces, you multiply those together and then divide by drawing 5 out of 52 cards. So what's the answer? That's 6 times 17,296. That's on top, and on bottom is 2,598,960, and that comes out to equal, it's a very long decimal, but we'll round off to 4 decimal places. We get 0.0399. That's the probability of getting 2 aces in a hand of 5 cards. Okay? And this kind of calculation that we did, that's called a hypergeometric calculation. Don't worry about why they call it that. That's just the name that we know it by. Okay? All right, so I can summarize all of this with a formula. Look at that sentence. The probability of getting X successes, in our case, a success was drawing an ace, so X was 2. That brings us up to here. Let's keep track of where we are in this sentence. Okay, then it says, in an attempts, well, how many cards were we drawing in that example? We were drawing 5, so little n is 5 in that example. Then it says, when capital A successes exist, well, how many aces exist in a deck of cards? 4 of them. So A was 4. In a population of capital N, how many cards are there in a deck? 52. So in our example, X was 2, drawing 2 aces. N was 5, we drew 5 cards total. Capital A was 4, there are 4 aces that exist in the deck. And capital N was 52 because there's 52 cards in a deck. Okay? Now here's the formula that we followed. We didn't know it at the time, but there's the formula that we followed. A choose X times capital N minus A choose little n minus X divided by capital N choose little n. Let's look up here and see that that's exactly what we did. So A choose X, that's 4 choose 2, we did that right here. And then N minus A choose n minus x. So that's 52 minus 4, which is 48. Choose 5 minus 2, which is 3. So we did that right there. And then on the bottom, we have capital N, choose little n. That's 52, choose 5. We did that right there. So this is exactly the formula that we followed. We just didn't know it at the time. Okay, and we will call that h of x. And h stands for hypergeometric. Don't worry about where that name comes from. That's not important to us. That's just the name that we know it by. That's all. Okay, so let's test ourselves by doing this example. It looks really long, but it's not. It's just the first 3 sentences. The rest of it is the explanation of how to do the problem. So there's the question right there. A candy dish contains 30 jelly beans and 20 gumdrops. 10 candies are picked at random. What's the probability that 5 of them are gumdrops? So they're asking us for h of 5, which equals, now I want us to write down all 4 of the important numbers here. I want us to write down x, n, a, and capital N. You should be in the habit of doing that. Okay? So what's x? It's the number of successes, and in this case, success is a gumdrop. And they're asking us for the probability of getting 5 gumdrops. So x would be 5 in this question. What is n? N is the number of attempts. How many things are we going to draw? Well, look what it says. 10 candies are picked at random, so n is 10. A is the number of successes that exist in the population. How many gumdrops are in the dish? 20 of them. And n is the number of the population. Well, how many candies are in the dish? 50 of them. So to answer this question, we should do 20, choose 5, times 50 minus 20, which is 30, choose 10 minus 5, which is 5, divided by 50, which is the total number of candies, choose 10, which is how many we're picking. And that's going to give us the answer. And you can use a calculator to do the calculations. Let's see. 20, choose 5, is 15,504. 30, choose 5, is 142,506. And 50, choose 10, is pretty huge. That is 102,722, 78170. So let's see. That's a little over 10 billion. Okay? And then we just multiply 15,504 times 142,506 divided by 10,272 278, 170. And we get an answer of, let's go ahead and stick with 4 decimal places. In that case, we would round off to 0.2151. Not too hard, right? Okay, let's do one more. Actually, what I'll do is I'll just move that one down so that we can still see the formula. Okay, let's do this example, also from the book. Okay. A bag contains letter tiles. 44 of the tiles are vowels. 56 are consonants. So let me ask you, how many are in the bag? 44 vowels and 56 consonants. That would be 100, right? 7 tiles are picked at random, and you want to know the probability that 4 of the 7 are vowels. It says what is the group of interest, the size of the group of interest, and the size of the sample. Okay, so the group of interest is the vowels, right? And the size of that is 44. The size of the sample is 7. But I think it'll be better if we just write this in terms of the same letters we used before. Let's write X, little n, capital A, capital N. Okay? So it says 7 tiles are picked at random. Well, there's the 7 then, is little n. You want to know the probability that 4 are vowels, so X is 4. Capital A is the total number of vowels, which would be 44. And capital N is the total number of tiles, as we said earlier, that must be 100. So we would write X of 4 equals 44, choose 4, times 100 minus 44, choose 7 minus 4, divided by 100, choose 7. All right, and then it's just a matter of doing those calculations. 44, choose 4 is 135,751. Okay, 56, choose 3, 27,720. And 100, choose 7. 16 billion 7,560,800. Okay, now 13,5,751 times 27,720 divided by 16 billion. Sorry, give me a second to get caught up here. I wasn't typing where I thought I was. Okay, divided by 16 billion 7,560,800, And our answer to 4 decimal places is 0.2351. Okay. If you have any questions on that, just let me know.